Okay, so now we are recording a lecture on Chapter 2 and Chapter 13 of your textbook for data architecture and modeling. This is also what we call as Lecture 2. So the first thing that we want to look at in this particular lecture is the important concept of information retrieval. Information could be stored in some place in some particular form. But the information that is stored and needed to be retrieved should be relevant to the problem. So that's one of the key things of information retrieval. That information must be relevant to the problem, and information retrieved must answer the required or the specific questions that we try to answer. Sometimes we walk into a meeting and then you want to talk on a particular specific topic. And then there are individuals who keep talking and talking about some different things that have nothing to do with the main objective of the meeting, and that leads to digression. Information retrieval should not be like that. Information retrieved should pertain to that specific problem or that specific question that we are trying to answer. So information retrieval can happen in the form of ontologies, in the form of decision tables, in the form of patient-specific information. Key developments in this area are already happening. So, there are different types of information formats, and depending on the type of information that is stored, different retrieval methods could be employed. So there could be a semi-automated search or an automated search. The parameters for search could be user-initiated based on the conditions provided by the user. That is a semi-automated search. The parameters for search could be automatically generated by the application, and that is an example for an automated search. So for example, if I go to Google and put in maybe electronic health record and click submit, boom, it goes on the websites and any content that is out there pertaining to electronic health records, because it searches for 3 different words: electronic health records. That's an example for user-initiated semi-automated search. In the case of an automated search, the computer program looks at, oh, this paragraph has this keyword, depression. Let me go and find out some information on depression. So this is how the application works, not the human being, the computer application. That's an example for automated search. Advanced questioning answer systems is possible due to the advent of natural language processing. We developed a system that automatically makes phone calls, asks patients certain questions, and then patients answer those questions using some keys on their phone and things like that. That's an example of automated search. Everything is automatic. So program can do an automated search, and a human initiated search is a semi-automated search. So you have decision tables. Here is an example for decision table: infant passengers. These are the rules 1 through 8. And for infant passengers aged less than 2, rules 1 and 2 apply. For youth passengers ages between 2 and 16, rules 3 and 4 apply. Frequent flyers, rules 5 and 6 apply. So you can see how things can be identified using decision tables. Venn diagrams are also used for decision making. You have whales and fish. There are certain similarities and certain things that are different. Fishes breathe water, whales breathe air. Both can swim, both have fins, both live in water. But there are differences and common things. So those things are represented using a Venn diagram. Then we have logical expressions. Here's an example for logical expression. A equal to 5, B equal to 10, C equal to minus 6, right? A is less than B and A is also less than C. So 5 is less than 10. And A is less than C, which is not the case in this particular example because minus 6 is less than A. So you have the next expression, which is A is less than B and A is greater than C. So that's correct in this particular example. So there are different ways in which a logical expression could define certain things or could express a few things mathematically. Then we have Bayesian networks. Visit to Asia may lead to tuberculosis. Smoking can lead to lung cancer or bronchitis. And you have tuberculosis and lung cancer both combined to form tuberculosis or cancer. You have to have an X-ray to find out if the person has tuberculosis. If you have tuberculosis, you may have shortness of breath. If you have bronchitis, also you may have shortness of breath. So you can see how we define causal relationships here. Causal relationship means one thing causes the other. For example, smoking can cause lung cancer and smoking can also cause bronchitis. This is what we call causal relationship. One thing causing the other. Visit to Asia can cause tuberculosis. So visit to Asia causes tuberculosis. That's a causal relationship between visit to Asia and tuberculosis. So this is how we identify causal relationship using Bayesian network. Then we have something called heuristic models. Now, Bayesian networks could also be used in heuristic models. Here's a cartoon that says, I know the last 5 scratch-off tickets didn't win, which means this next one must be a winner. That's heuristics, educational guessing. If you have 6 tickets, and you know for a fact that one of them is a winner, the first 5 did not win, what that tells you is the last one is a winner. Okay, that's heuristics, educational guessing. Here's an example, ST segment changes. Yes, take the patient to coronary care unit. If the answer is no, chief complaint of chest pain, the answer is yes. Do this, otherwise take the person to regular nursing bed. And if the answer is yes for any other factor, then take the person to coronary care unit or take the person to regular nursing bed. So that's heuristic model. I mean, you make a guess here. Maybe this person does not have a serious problem. Maybe. It sounds like. Or it sounds like the person has a serious problem and has to be taken to an emergency care unit. So you make education guessing. In a clinical setting, there's always the case. You don't know what is happening with the patient initially. You make an educated guess, and then you move forward. You conduct the test, and based on the test, you make further decisions. So architecting data is very important in all these cases, as you can see. Then we have the bigger animal here, population health data. We are not talking about an individual data as we have seen in the previous cases. We're now talking about the population health data. Health system-based registries record information about patients seen in a particular facility or health system. What that tells you is, this is an area where people from Ebola, this is an area of the city where people are infected by Ebola virus. So quarantine this part of the city. That's population health data. And that's very important in outbreak of epidemic and those type of things. Analysis of information about the data becomes possible, and you develop population-based registries. For example, West Dallas had some problem with pollution for a long time. And because of that problem in pollution in the western part of Dallas, people were suffering from particular type of diseases more frequently than people living in other parts of Dallas. And because of that information, in the 90s, I don't remember whether it was the state government or the federal government, one of those two, or together, they took measures to make sure that this pollution problem was taken care of to improve the health care of residents of West Dallas. So this is how population health data can be very useful. Database development is very important to analyze population health data, and database development and working with databases is actually not a part of this course curriculum. We have a different course for databases, and I hope, I'm not sure if you are already taking that course or you already taken that course, depending on which cohort you belong to. But if you know databases, you'll know why it is important, okay? Because it can be helpful in performing analysis, development of registries, etc., etc. So big data analytics and population analytics is an upcoming field, but they are not the same. Big data refers to massive volume of unstructured and structured data. So we already discussed what is unstructured data, and we already discussed what is structured data in the previous lecture. The three verses associated with big data are, or the three V's, sorry, the three V's associated with big data are volume, velocity, and variety. Volume refers to the volume of available data that is exponentially rising. I can give you one example here. I was working for a particular department that was dealing with brain images. And a doctor asked me, how much storage do I want to store all the brain images? I asked him, how many brain images do you have? And he told me, I don't know, I keep getting brain images every day, and it's like water flowing. I said, oh my God, I don't have an answer to that question, because you probably need a big server farm that can store all the information. But let's start with 1 terabyte. I don't know where he is right now and what is happening with his brain images, but that's how it is. Velocity refers to the rate at which data is created. Again, going back to that brain image example, how many brain images were coming in every single day, how many brain images were coming in every month. That's velocity. Variety refers to the fact that data types that are stored are more variable than ever before. So there could be a brain image data coming in, there could be an X-ray data coming in, there could be like a text file coming in. So that's variety. So decision support to improve population health is important, and that's where data architecture and modeling comes into picture. As I said, outbreak of epidemic diseases like influenza, digital disease detection for surgical sites, robotic surgery, all that data has to be structured in a particular way, and that's where things that you learn in this course come handy. Okay, data for decision support to implement interventions. Treating diseases using evidence-based medicine is important. Evidence-based medicine means you found out something new, and there is some heuristics involved, that if a person has this, then there's a 90% chance that the person also has this. So if you have that data ready, you could probably have a better guess if you are a clinician. Review of medical records for potential preventive and disease management needs. This is again going back to this person has a history of stroke, then you got to be careful. If the person has a family history of diabetes, you got to be careful. Don't treat this patient with a lot of sugary stuff. Proactive care can be implemented by periodic reminders, facilitation of tracking over time. For example, you could have a medication reminder. You could have a software that asks a person simple stuff like, what did you eat today? How many pizzas did you have today? And then, oh, by the way, I had, a pizza in the morning and I had a pizza in the afternoon. And that's not good. So then the system can send the information to the doctor, hey, your heart patient is eating too many pizzas. So you might want to watch out for this guy. Especially if that heart patient is dealing with an MSO. So, all these things are very important. Medication stewardship includes knowledge of current profiles of antimicrobial agent prescribing practices and their outcomes. Available data on interventions could be used to improve interventions using EHRs. For example, this intervention works well on a person of this ethnicity. This intervention probably does not work well for a person of this ethnicity. Sometimes genetic makeup of that particular individual can lead to a particular type of prescription being used on that particular individual. Those things can play a handy role. So these are complicated topics, but decision support based on previously captured data could be very useful. Okay, so that ends lecture 2. Thank you very much.